Welcome to our deep dive today. We're going to be tackling some really intriguing mathematical concepts,
Yeah.
and we're going to be drawing all of this from a textbook called Thinking Mathematically.
Yeah.
And get ready, because we're going to see how math can be used to understand things like the likelihood of a hurricane hitting South Florida,
Oh, wow.
or even the cost of making a penny.
That's right. We'll be looking at how math is more than just numbers. It's about logic and problem-solving strategies that can be applied to so many real-world scenarios.
Yeah, absolutely. Okay, so let's unpack this, starting with number patterns and logic.
Okay.
The textbook gives us this example of finding the next number in a sequence.
All right.
It's 3, 12, 4, 8, 192, 768. What comes next?
Well, using inductive reasoning, we can see that each number is 4 times greater than the one before it. So the next number should be 3072.
That's exactly right.
Okay.
But the book doesn't stop at simple sequences.
Right.
It presents this brain teaser. Pick a number, any number, multiply it by 6. Add 8, divide by 2, and then subtract 4. Can you guess what the relationship is between your starting number and the final result?
It's a fun challenge, right? But through deductive reasoning and a bit of algebra, the textbook proves that no matter what number you start with, the final result will always be 3 times the original number.
Yeah,
And it's really neat how it breaks that down step by step.
it really is. It highlights how math is all about logic and proof.
Yeah.
Speaking of proof, let's dive into some real-world applications of statistics.
Okay.
The textbook has this interesting graph showing how Americans define old age.
Okay.
And it turns out most people define it as a decline in physical ability, not reaching a certain age, which was the least common response.
Interesting. That's a great example of how statistics can reveal perceptions. And then it takes it a step further by connecting this to life expectancy trends shown in another graph.
Yeah.
It actually uses that graph to estimate future life expectancy based on the year someone was born.
So if you were born in, let's say, 1990, the graph suggests you could live to be around 85. Does that surprise you at all? It makes you think about how those statistical predictions could influence your own plans for the future, right?
Absolutely.
Uh,
Now let's move on to sets and Venn diagrams, which are all about visualizing relationships. Think of sets as collections of anything,
Yeah.
numbers, colors, even movie preferences.
right.
And subsets are just smaller sets within those larger sets.
Right. I remember Venn diagrams from school.
Yeah,
They use overlapping circles to show how elements in different sets relate to each other.
exactly.
Yeah.
The textbook has a problem involving people who like comedies, dramas, and science fiction movies.
Okay.
The Venn diagram clearly shows how some people might like all 3 genres,
Yeah.
while others only enjoy 1 or 2.
So Venn diagrams are helpful visual tools for organizing information even beyond math. I never thought of them that way before. Could you give me an example of how they might be useful in the real world?
Well, imagine you're a marketing manager trying to understand your customer base. You could use a Venn diagram to represent different customer segments based on their interests, demographics, or purchasing habits. This could help you tailor your marketing strategies to specific groups and potentially increase your sales.
That makes a lot of sense. Okay, let's move on to a topic that can be a bit daunting. Logic and truth tables.
Yeah. The textbook does a great job of simplifying it. It starts by introducing symbolic logic, where letters represent statements, kind of like a code. For instance, the letter P could represent the statement, "Today is Monday."
Okay, I'm following so far. And then it gets into negation, which basically means the opposite of a statement, right?
Precisely. The negation of P would be, "Today is not Monday." It uses the symbol to represent not.
So if we use Q to represent it's raining, then Q would mean it's not raining. Got it. But then things get a bit more complex with truth tables.
Truth tables are a way to systematically analyze the truth or falsity of statements and how they combine. Imagine a table that lists all the possible combinations of true and false for the statements you're considering. Then using logical operators like and or, you can determine the truth value of more complex statements based on those combinations.
Okay, so let's say R represents I have an umbrella. A truth table could show us what happens logically in different scenarios. If
Yeah.
it's raining and I have an umbrella, or if it's not raining and I don't have an umbrella, and so on.
Exactly. Truth tables can be used to analyze everything from simple everyday scenarios to complex arguments in philosophy or even legal cases.
Wow, I never realized how powerful truth tables could be. But the textbook does mention they can get surprisingly complex when you start adding more statements, right?
Absolutely.
Yeah.
As you add more variables, the number of possible combinations grows exponentially. It's like those logic puzzles where each clue adds another layer of complexity. But that's where the power of truth tables really shines. They provide a systematic way to navigate that complexity.
That's fascinating. Okay, let's move on to the topic of arguments and validity. Now, I'm assuming this isn't about who's winning a shouting match, right?
Right. It's about analyzing the logical structure of arguments to see if the conclusion follows logically from the premises. The textbook uses a really fun example featuring Mr. Spock from Star Trek to illustrate this.
Wait, are you telling me Mr. Spock, the epitome of logic, might have made a logical error? I need to hear this.
Well, the book focuses on Spock's statement, "If the power is on, then Mr. Scott is still with us." It seems logical on the surface, but when you break it down using symbolic logic in a truth table, you discover that the argument is actually invalid.
Okay, now I really need to know how that works. Let's dive into the details.
Let's break it down. We can represent the power is on with the letter P, and Mr. Scott is still with us with the letter Q. So Spock's statement becomes, if P, then Q.
Okay, I'm following so far. So how does that translate into an invalid argument?
Well, the argument also includes the premise, the power is on, which is just P. The conclusion is, Mr. Scott is still with us, which is Q. So the whole argument can be represented as, if P, then Q and P, therefore Q.
Seems logical, right?
It does. So where's the flaw?
When you build a truth table for this argument, it reveals that there's a scenario where both premises are true, but the conclusion could be false.
So even Mr. Spock, the master of logic, can make a logical error. I guess it just proves that we all need to be critical thinkers, even when things sound convincing on the surface.
Exactly, and that's what makes this section of the textbook so interesting. It helps you develop those critical thinking skills.
Absolutely. Now, before we move on to our last topic for this part of our deep dive, I have a question. Are truth tables the only way to analyze the validity of arguments?
Actually, there are other methods, and the textbook introduces one called Euler diagrams. They're named after Leonhard Euler, a brilliant mathematician. Like Venn diagrams, they use circles, but the focus is on using them for logical deductions.
So how do these Euler diagrams work? Well, let's say we have the argument. All college freshmen live on campus. No people who live on campus can own cars. Therefore, no college freshmen can own cars. An Euler diagram would use 3 circles to represent college freshmen, people who live on campus, and people who own cars.
I can picture that. So you'd put the college freshman circle completely inside the people who live on campus circle because the first premise states that all freshmen live on campus.
Exactly. And since the second premise says no one living on campus can own a car, the people who live on campus circle and the people who own cars circle wouldn't overlap at all.
Okay, that makes sense. So looking at this diagram, the conclusion, no college freshman can own cars, seems to be true, right?
It does in this specific diagram. But that's where things get interesting. Euler diagrams help us explore different interpretations of an argument. We could draw another diagram where the people who own cars circle overlaps with the people who live on campus circle, but not the college freshman circle.
Ah, I see what you're saying. So even though the first diagram makes the argument seem valid, there's another possibility where the conclusion doesn't hold true. That means the argument itself is actually invalid.
That's right. Euler diagrams help us visualize different interpretations of an argument and test its validity by seeing if the conclusion holds true in every possible scenario.
This is definitely making me think about arguments in a whole new way. Okay, let's move on to our final topic for this part of our deep dive, number systems.
All right.
This section is fascinating because it takes us on a journey through history,
Yeah,
exploring how humans have developed different ways to represent numbers.
that's right.
The book begins by discussing ancient civilizations and their unique number systems,
Okay.
like the Babylonian system, which used a base 60 system, right? Instead of grouping things in tens like we do,
Yeah.
they used groups of 60.
That's right. And they only had 2 symbols, a wedge shape for 1 and a crescent shape for 10. It's amazing how they managed to represent large numbers using just those 2 symbols and a positional system.
You know, the concept of 0 as a placeholder seems obvious now, but imagine trying to do math without it.
Right.
The Babylonians didn't have a symbol for 0, which must have made things quite difficult.
It certainly limited their calculations and created ambiguity, but their system highlights the ingenuity of early civilizations and their efforts to develop ways to quantify and understand the world around them.
It really makes you appreciate the elegant and efficient system we use today. Okay, I'm ready to explore more of these fascinating number systems. What's next?
Next, we have the Mayan system.
Okay.
Next, we have the Mayan system. They used a base 20 system, probably because they used both fingers and toes for counting.
That makes sense.
The-
So did they have a symbol for 0?
Yes, they did. The Mayans were one of the first civilizations to develop a symbol for 0, which allowed them to represent large numbers and perform complex calculations.
It's incredible how such a seemingly simple concept like zero revolutionized math. It's like a missing piece of a puzzle that unlocks a whole new level of understanding.
Absolutely. The invention of zero was a profound breakthrough in human thought. It allowed us to move beyond concrete quantities and grapple with abstract concepts.
So, from the Babylonian-based 60 system to the Mayan-based 20 system, we see how different cultures developed unique ways to represent numbers.
And that brings us to the system we use today, the Hindu-Arabic numeral system. It originated in India and was later adopted by Arab mathematicians who spread it throughout the world.
The textbook says this system was a game changer because it combined a base 10 system with unique symbols for the digits 0 through 9 and a positional system where the value of a digit depends on its place. It seems so simple and efficient.
It is.
Oh.
It made calculations easier and paved the way for advancements in mathematics, science, and engineering. It's hard to imagine where we'd be without it.
Speaking of making things easier, the textbook also delves into problem-solving strategies. I'm always looking for ways to improve my problem-solving skills. What does the book suggest?
It focuses on a framework developed by George Pulya, a famous mathematician. His approach breaks down problem solving into 4 steps: understanding the problem, devising a plan, carrying out the plan, and then looking back to check your work and see what you can learn from the process.
So it's not just about finding the right answer, it's also about reflecting on how you got there.
Exactly. And the best part is that Pulya's method can be applied to any problem, not just those in math. It's a valuable tool for approaching challenges in any area of life.
Okay, I can definitely see how that would be helpful. Does the book give any examples of how to use this problem-solving framework?
It uses the real-world problem of a sales director needing to visit 4 different cities and wanting to find the cheapest route. The book presents a table showing the airfares between each city.
So you could just try calculating the cost of every possible route, but that sounds pretty tedious.
It is, and that's where Pulya's method comes in. The book suggests using a visual diagram, like a network, to represent the connections between the cities and their airfares.
I can see how a visual representation would be much easier to work with than just a table of numbers.
Absolutely. It allows you to see the relationships and possibilities in a more intuitive way. The book then uses this diagram to systematically explore different routes and find the most cost-effective one.
That's a great example of how visual tools can be incredibly helpful for problem solving. It's like the saying, a picture is worth 1,000 words, but in this case, it's a picture is worth 1,000 calculations.
Exactly. Now let's dive back into the world of sets. Remember, we talked about finite sets, which have a limited number of elements. Well, the book also introduces infinite sets, which go on forever. It's a mind-boggling concept.
Infinity is definitely a challenging concept to wrap your head around. But the book also talks about equal sets, which seem a bit more manageable.
Right. Equal sets contain the exact same elements, even if they're listed in a different order or if there are repetitions.
So if I have a set with the numbers 1, 2, 3, and another set with the numbers 3, 2, 1, those are considered equal sets.
Exactly. The order doesn't matter, and neither does the repetition of elements. The key is that they contain the same elements.
Okay, that makes sense. Now, what about subsets? We touched on those briefly with Venn diagrams.
A subset is a set where all its elements are also elements of another larger set. Think of it like a smaller box fitting inside a bigger box.
And a proper subset is one that's smaller than the set it's contained in, right?
You got it. For example, let's say we have set A with the elements 2, 4, 6, 8, and set B with the elements 2, 8, 4, 6, 6, 4, 2.
So set A is a subset of set B because all of its elements are also in set B, but it's not a proper subset because it contains all the same elements as set B, even though set B has some repetitions.
Precisely. You're getting the hang of this. Now let's revisit Venn diagrams. The textbook presents a problem where 60 people are surveyed about their movie preferences, comedies, dramas, and science fiction. You're given information like 12 people like comedies and dramas, or 25 people like science fiction.
Okay, I remember these types of problems. They can be a bit tricky to keep track of all the information.
That's where the power of Venn diagrams really shines. The book shows how to systematically fill in each section of the diagram, starting with the overlaps and working your way out.
It's like solving a puzzle, but instead of pieces, you're using numbers and logic.
Exactly. The Venn diagram helps you visualize and keep track of all the information. It even shows you how to determine how many people liked only one genre, or combinations of genres.
I can see how this type of problem solving would be useful in so many real-world situations. Imagine trying to analyze survey data or understanding market segments without a tool like a Venn diagram.
Absolutely. They provide a clear and intuitive way to organize and interpret complex data.
Okay, I'm ready for another deep dive into symbolic logic and truth tables. That last example with Mr. Spock really piqued my interest.
Great. Let's recap. Remember that in symbolic logic, letters represent statements, and we use symbols like for not, for and V for or.
Right. And negation symbolized by P means it's not true that P is true.
Exactly.
Yeah.
For example, if P represents the statement, the cat is on the mat, then P means the cat is not on the mat.
So how do truth tables fit into all of this?
Truth tables help us systematically determine the truth value of compound statements based on the truth values of their individual parts. It's like a logical recipe that shows us all the possible outcomes.
Okay, I'm ready for a more challenging example. What does the textbook offer?
It uses the example of studying missing lectures and failing a course. The statement is, if a student studies and does not miss lectures, then the student does not fail. We can represent this symbolically as QPR, where Q means the student studies, P means the student misses lectures, and R means the student fails.
Okay, that's a lot of symbols. So how does the truth table help us analyze this statement?
The truth table lists all the possible combinations of true and false for P, Q, and R. It then uses the logical operators to determine the truth value of the entire statement for each combination.
So the truth table shows us whether the statement, if a student studies and does not miss lectures, then the student does not fail, is true or false in every possible scenario.
Exactly. It's a powerful tool for breaking down complex logical statements and seeing exactly when they hold true or not.
This is really making me think about how logic underpins so much of our thinking, even when we don't realize it.
You're right. Logic is the foundation of reasoning, and it plays a crucial role in everything from solving problems to making decisions to constructing arguments.
Okay, I'm ready to revisit Mr. Spock and see how truth tables can reveal the flaws in seemingly logical arguments.
Excellent. The book uses Spock's statement, if the power is on, then Mr. Scott is still with us, to demonstrate how to determine the validity of an argument using a truth table.
We already represented this statement as if P then Q, where P is the power is on and Q is Mr. Scott is still with us. So how do we build a truth table to analyze the validity of the entire argument?
Remember, the argument also includes the premise, the power is on, which is just P, and the conclusion, Mr. Scott is still with us, which is Q. So the entire argument is if P then Q and P therefore Q. We can represent this symbolically as PQ, PQ.
Okay, so the truth table will show us the truth values of this entire statement for all the possible combinations of true and false for P and Q.
Precisely. And here's where it gets interesting. The truth table reveals that there's one scenario where the premise is if P, then Q and P are both true, but the conclusion Q is false.
So even though the argument sounds logical, the truth table shows us that it's actually invalid because there's a case where the conclusion doesn't necessarily follow from the premises.
That's right. It's a great example of how truth tables can help us identify logical fallacies, even in seemingly sound arguments.
This is really making me want to go back and analyze all those arguments I've had over the years.
It's a great exercise in critical thinking. And speaking of critical thinking, it's important to remember that truth tables aren't the only tool for analyzing arguments. We also have Euler diagrams, which offer a visual way to explore different interpretations.
Right. We saw how those can be helpful for identifying the validity of arguments, especially those involving quantifiers like all, some, or none.
Exactly. And it's worth noting that truth tables and Euler diagrams aren't mutually exclusive. They can be used together to provide a more comprehensive understanding of an argument's logic and validity.
That makes a lot of sense. Combining different perspectives can often lead to richer insights. Okay, I'm ready to continue our exploration of number systems. We've talked about ancient civilizations and their unique systems, but what about our own decimal system, or base 10?
It's a system that's so ingrained in our thinking that we rarely stop to appreciate its brilliance. It uses 10 unique digits 0 through 9, and each digit's value depends on its place value, which is based on powers of 10.
So the rightmost digit represents the ones place 100, then the tens place 101, the hundreds place 102, and so on.
Exactly. For example, the number 357 represents 3 hundreds, 302, 5 tens, 501, and 7 ones, 7 100. It's a system that has allowed us to make incredible advancements in science, technology, and countless other fields.
It's amazing how such a simple concept has had such a profound impact on human civilization. Okay, I'm ready for a challenge. The book mentions other number bases like binary base 2 and hexadecimal base 16. Can you explain those?
Absolutely. Binary is a base 2 system that uses only 2 digits, 0 and 1. Each place value represents a power of 2, starting with the rightmost digit as the 1's place, 20, then the 2's place, 21, the 4's place, 22, and so on.
So how would we convert a binary number to a decimal number?
Let's take the binary number 1011 as an example. It represents 1 8, 123, 0 4s, 0 22, 1 2, 121, and 120. Adding those together, we get 8 plus 0 plus 2 plus 1 equals 11 in decimal form.
That's pretty amazing. And why is binary so important?
It's the language of computers. All data in a computer is stored and processed as strings of zeros and ones representing the on and off states of electronic switches. It's like a secret code that underpins our entire digital world.
Okay, that is mind-blowing. It's like these abstract mathematical concepts are the foundation for so much of our modern world.
Exactly. And then we have hexadecimal, a base 16 system that uses 16 digits 0 through 9, and then A, B, C, D, E, and F to represent the values 10 through 15.
So instead of place values being powers of 10, they're powers of 16.
Precisely. Each place value represents a power of 16.
Go
So the hexadecimal number 2A represents two 16s, 2 161, and 10 ones, A160, which adds up to 32 plus 10 plus 10, 42 in decimal form.
Okay, I think I'm starting to get the hang of this.
Yeah.
But why do we need hexadecimal if we already have binary?
Hexadecimal is often used in computer programming and digital design because it provides a compact way to represent binary data. Each hexadecimal digit corresponds to 4 binary digits, making it easier for humans to read and write large binary numbers.
So it's like a shorthand for binary that makes it more manageable for us humans to work with?
Exactly. It's a great example of how we use different number systems for different purposes depending on the context and the task at hand.
This deep dive into number systems has been fascinating. We've gone from ancient civilizations to the binary code that runs our computers. It's incredible how diverse and interconnected the world of numbers is.
It truly is. And it highlights the power of human creativity and our enduring quest to understand the patterns and structures that shape our universe.
Well, I'm definitely feeling a bit overwhelmed by all these different number systems. Maybe we can shift gears a bit and explore some foundational concepts of number theory.
Sounds like a plan? Let's start with divisibility rules, which are shortcuts for determining if one number divides evenly into another.
Oh, like the rule that a number is divisible by 2 if its last digit is even, and it's divisible by 5 if its last digit is a 0 or a 5.
Exactly. Those rules can be quite helpful for simplifying fractions, factoring numbers, and solving various math problems.
I remember learning those in school. They can definitely save you a lot of time and effort.
They certainly can. Now let's talk about prime numbers. These are whole numbers greater than 1 that are only divisible by 1 in themselves.
So numbers like 2, 3, 5, 7, 11, and so on.
Precisely. Prime numbers are like the building blocks of all other whole numbers. Any whole number can be expressed as a unique product of prime numbers, which is known as the fundamental theorem of arithmetic.
That's pretty amazing. It's like every whole number has a unique fingerprint made up of prime numbers.
That's a great way to think about it. Now, what do we call the whole numbers that aren't prime?
Those are composite numbers, right? Numbers that have more than 2 factors.
You got it.
Yeah.
Essentially, all whole numbers greater than 1 are either prime or composite. Now let's delve into some concepts that relate to prime and composite numbers. The greatest common factor, GCF, and the least common multiple, LCM.
Okay, I remember those terms from somewhere, but could you refresh my memory?
The greatest common factor, GCF, is the largest number that divides evenly into 2 or more numbers. It's like finding the biggest piece that fits perfectly into 2 different puzzles.
I can see how that would be useful for simplifying fractions.
Exactly. For example, the GCF of 12 and 18 is 6. We can use this to simplify the fraction 12/18 to 23.
That makes sense. Now, what about the least common multiple, LCM?
The least common multiple, LCM, is the smallest number that is a multiple of 2 or more numbers. It's like finding the smallest box that can hold 2 different sets of items.
So if we're looking for the LCM of 4 and 6, it would be 12, right? Because 12 is the smallest number that is divisible by both 4 and 6.
You're right. The LCM is helpful for finding common denominators when adding or subtracting fractions and for solving problems involving repeating patterns or cycles.
I can see how that would be useful in real-world situations involving scheduling or planning events.
Absolutely.
Yeah.
The GCF and LCM are surprisingly versatile concepts that can be applied to a wide range of problems.
Okay, so we've covered prime numbers, composite numbers, the GCF, and the LCM. What's next on our number theory journey?
Let's do a quick review of basic operations with integers. Remember, integers are whole numbers and their opposites, including 0.
I remember learning about adding, subtracting, multiplying, and dividing integers, but it can be tricky to keep all the rules straight, especially when working with negative numbers.
You're right, it can be confusing,
Mm.
but the rules are actually quite simple once you understand the underlying concepts. For example, when adding integers with different signs, you subtract their absolute values and keep the sign of the number with the larger absolute value.
So to add magnetic 7 plus 3, you subtract 3 from 7 and keep the negative sign, because negative 7 has a larger absolute value than 3. The sum is magnat 4.
Exactly. You've got it. And when subtracting integers, it's often helpful to think of it as adding the opposite.
So to subtract 5, McGrath, we can rewrite it as 5 plus 2, which gives us 7. That makes it much easier to visualize.
Right, and remember the rules for multiplying and dividing integers. When multiplying or dividing two numbers with the same sign, the result is always positive. When multiplying or dividing two numbers with different signs, the result is always negative.
Okay, I think I've got those rules down. Why is it so important to master these basic operations with integers?
They form the foundation for more complex algebraic operations. If you don't have a solid grasp of these rules, you'll likely struggle with algebra, calculus, and more advanced mathematical concepts.
That makes a lot of sense. It's like building a house, you need a strong foundation to support the rest of the structure.
Precisely. Now that we've covered integers, let's move on to rational numbers. The book defines rational numbers as numbers that can be expressed as a fraction, where the numerator and denominator are both integers.
So numbers like 12, 34, and 5, which can be written as 51, are all rational numbers.
That's right. And it's important to remember that terminating decimals, those decimals that end neatly, and repeating decimals with a repeating pattern, can also be expressed as fractions, making them rational numbers as well.
So 0.25 can be written as 14, and 0.333 can be written as 13.
Exactly. Now, what about operations with rational numbers? Remember how we simplified fractions by finding the greatest common factor, GCF?
Yes. And to multiply fractions, you multiply the numerators and multiply the denominators. To divide fractions, you invert the second fraction, flip the numerator and denominator, and then multiply.
You're on a roll. And how do we add and subtract fractions with different denominators?
We need to find a common denominator, which is usually the least common multiple LCM of the denominators.
Excellent. It's a lot to remember, but with practice, these operations become second nature.
And mastering these operations is essential for success in algebra, geometry, and more advanced mathematical concepts, right?
Absolutely. Now, prepare to enter the mind-boggling world of irrational numbers.
Ooh, irrational numbers. Those are the ones that can't be expressed as a fraction of two integers, right?
You got it. The most famous example is pi, the ratio of a circle's circumference to its diameter. Its decimal representation goes on forever without repeating.
Pi is definitely one of the most well-known mathematical constants. It seems almost magical how it keeps going and going without any pattern.
It is fascinating. The book also mentions other irrational numbers like the square root of 2, which also can't be represented as a terminating or repeating decimal. These numbers exist on the number line, but we can't pin them down precisely with a fraction.
It's like they defy our attempts to categorize and define them. They exist in this realm between the rational and the unknown.
That's a great way to put it. And together, rational and irrational numbers make up the set of real numbers, which encompasses all the numbers we typically encounter in mathematics.
So the world of numbers is much more vast and complex than we might realize at first glance.
Absolutely. It's a world full of wonder and endless possibilities for exploration and discovery.
Okay, I think we need a little break from all these numbers. Can we move on to something a little more visual?
Sure, let's explore how mathematics can be used to understand and appreciate the beauty of geometric shapes.
That sounds fun. I've always been fascinated by the elegance and symmetry of geometric patterns.
It is captivating. The textbook starts with the basic building blocks of geometry: points, lines, and planes. A point is a location in space with no size or dimension. A line is a straight path that extends infinitely in both directions. And a plane is a flat surface that extends infinitely in all directions.
Those are the fundamental elements that we use to construct all sorts of geometric shapes, right?
Exactly. And the book then delves into different types of lines, like parallel lines which never intersect, and perpendicular lines which intersect at a 90-degree angle.
I remember learning about those parallel lines always remind me of railroad tracks.
That's a great analogy. The book also discusses angles which are formed by two rays that share a common endpoint. It covers different types of angles, like acute angles, which are less than 90 degrees, obtuse angles, which are greater than 90 degrees, but less than 180 degrees, and right angles, which are exactly 90 degrees.
Okay, I'm following along. So where do shapes come into all of this?
Shapes are formed by combining lines and angles in specific ways. The book starts with polygons, which are closed figures made up of line segments.
So triangles, squares, pentagons, hexagons, and so on.
Precisely. Each polygon has a specific number of sides and angles. The book explores different properties of polygons, like the sum of their interior angles and their perimeter, which is total length of all the sides.
I remember those formulas from geometry class. They can be quite handy for calculating areas and lengths.
They certainly can. The book then moves on to circles, which are defined as the set of all points in a plane that are a fixed distance from a given point called the center.
I've always been fascinated by circles. They seem so simple, yet so perfect.
They are. And the book explores various properties of circles, including their circumference, which is the distance around the circle, their diameter, which is the distance across the circle through the center, and their radius, which is the distance from the center to any point on the circle.
I remember those terms. And there's a special relationship between the circumference diameter and pi, right?
Exactly. The circumference of a circle is always pi times the diameter. It's a remarkable relationship that connects this fundamental geometric shape to this enigmatic, irrational number.
It's almost poetic how math can reveal these hidden connections between seemingly disparate concepts.
It is, and the book doesn't stop there. It delves into three-dimensional shapes or solids like cubes, spheres, cylinders, cones, and pyramids.
Okay, now we're really venturing into the realm of 3D. It's hard to imagine visualizing these shapes without some sort of visual aid.
You're right. That's why the book uses diagrams and illustrations to help you visualize these solids and understand their properties like their volume, which is the amount of space they occupy, and their surface area, which is the total area of all their faces.
I can see how those concepts would be important in fields like architecture, engineering, and design.
Absolutely. Understanding the properties of three-dimensional shapes is essential for creating structures, designing products, and solving a wide range of practical problems.
This deep dive into geometry is really opening my eyes to the beauty and utility of mathematical concepts. I'm starting to see how math is so much more than just numbers and formulas. It's a language that helps us understand and appreciate the world around us.
I couldn't agree more. Math is a powerful tool for exploring patterns, relationships, and structures in the natural world and beyond.
Okay, I'm ready for a new adventure. What other mathematical wonders await us in this textbook?
Let's delve into the fascinating world of algebra, where we use letters and symbols to represent unknown quantities and solve equations.
Algebra. I remember it being a bit of a challenge in school, but I'm ready to give it another try.
That's the spirit. Algebra might seem intimidating at first, but it's actually a very logical and systematic way of thinking. The book starts by introducing the concept of variables, which are letters that represent unknown values.
So instead of working with specific numbers, we're working with these placeholder letters that can represent any number.
Exactly. It's a powerful concept that allows us to generalize mathematical relationships and solve for unknowns.
Okay, I'm intrigued. How does the book approach this concept of variables?
It uses a simple example. Suppose you have a bag of marbles, and you add 3 more marbles to the bag. If you let m represent the original number of marbles in the bag, then the total number of marbles in the bag is m plus 3.
Okay, that makes sense. So the variable m allows us to express the total number of marbles without knowing the specific value of m.
Precisely. And the book then introduces the concept of equations, which are statements that 2 expressions are equal.
So something like m plus 3 equals 7.
Exactly. That equation tells us that the expression m plus 3 is equal to the value 7. And the goal of algebra is often to solve for the unknown variable, in this case m.
So how would we solve for m in that equation?
We can use algebraic operations to isolate the variable on one side of the equation. In this case, we can subtract 3 from both sides of the equation to get m equals 4.
So if we originally had 4 marbles in the bag and we added 3 more, we would have a total of 7 marbles.
Exactly. Algebra allows us to solve for unknown quantities in a systematic and logical way.
Okay, I'm starting to see how algebra can be a powerful tool. But the book mentions that algebra can get much more complex than this simple example, right?
Absolutely. Algebra encompasses a wide range of concepts and techniques, from solving linear equations to working with quadratic equations, polynomials, and even systems of equations.
Wow, that sounds like a lot to take in. Does the book provide any strategies for tackling these more complex algebraic challenges?
It does. It emphasizes the importance of understanding the order of operations, using inverse operations to isolate variables, and applying the distributive property to simplify expressions. It also introduces the concept of factoring, which involves breaking down expressions into simpler components.
I remember those concepts from algebra class, but they definitely require practice and careful attention to detail.
You're right. Algebra is a skill that develops over time with consistent effort and a willingness to embrace challenges.
Okay, I'm feeling ready to tackle some algebraic problems. What else does the book cover in this section on algebra?
It delves into the fascinating world of functions, which are mathematical relationships, where each input has exactly one output. It's like a machine that takes in a value and produces a corresponding output based on a specific rule.
So if we have a function where the rule is multiply the input by 2 and we input the value 3, the output would be 6.
Exactly. The book explores different ways to represent functions, including using tables, graphs, and equations.
Mhm.
It also discusses different types of functions, like linear functions, which produce graphs that are straight lines, and quadratic functions, which produce graphs that are parabolas or U-shaped curves.
I remember learning about those types of functions. They can be used to model all sorts of real-world phenomena like the trajectory of a ball thrown into the air or the growth of a population over time.
You're right. Functions are incredibly versatile mathematical tools that have applications in virtually every field of study, from physics and engineering to economics and biology.
This deep dive into algebra is really making me appreciate the power and beauty of this branch of mathematics. It's like a new language that allows us to express relationships, solve problems, and model complex systems.
I couldn't agree more. Algebra is a fundamental part of the mathematical landscape, and it provides a foundation for exploring more advanced mathematical concepts.
Well, I'm definitely feeling like my brain is getting a workout today.
That's a good sign. It means we're stretching our minds and expanding our understanding of the world through mathematics.
Okay, what's next on our mathematical adventure?
Let's explore the world of exponents and logarithms, which are powerful tools for dealing with very large or very small numbers.
Exponents, I remember those from school. They're those little numbers written above and to the right of a base number, and they tell us how many times to multiply the base number by itself.
That's right. For example, 23 means 222, which is equal to 8. The exponent 3 tells us to multiply the base number 2 by itself 3 times.
Okay, I'm following so far. But what about logarithms? They always seemed a bit mysterious to me.
Logarithms are essentially the inverse of exponents. They tell us what exponent we need to raise a base number to in order to get a specific value.
Okay, can you give me an example to help me understand that?
Sure. Let's say we have the equation 102 equals 100. The logarithm of 100 with base 10 is 2. We write this as log 10, 100, 2. It tells us that we need to raise the base 10 to the power of 2 in order to get 100.
Okay, I think I'm starting to see the connection between exponents and logarithms. But why are they so important?
They're incredibly useful for dealing with very large or very small numbers. For example, in science, we often encounter quantities like the speed of light or the size of an atom, which are either extremely large or extremely small. Exponents and logarithms allow us to express these quantities in a more manageable way.
That makes sense. It's like using a different scale to measure something very large or very small.
Exactly.
Yeah.
And the book delves into the properties of exponents and logarithms, showing how we can use them to simplify expressions, solve equations, and even model exponential growth and decay.
Okay, I'm starting to see how these concepts can be incredibly powerful tools for understanding and manipulating numbers.
They are. And they have applications in a wide range of fields, from finance and economics to physics and chemistry.
This deep dive into exponents and logarithms is really expanding my horizons. What other mathematical wonders await us in this textbook?
Let's explore the fascinating world of sequences and series, where we examine patterns of numbers and their sums.
Sequences, I remember those from the beginning of this deep dive where we figured out the pattern in a series of numbers.
That's right. A sequence is simply an ordered list of numbers, and a series is the sum of the terms in a sequence.
So if we have the sequence 1, 3, 5, 7, the corresponding series would be 1 plus 3 plus 5 plus 7, which equals 16.
You got it. The book explores different types of sequences, including arithmetic sequences, where the difference between consecutive terms is constant, and geometric sequences, where the ratio between consecutive terms is constant. That's right. A sequence is simply an ordered list of numbers, and a series is the sum of the terms in a sequence.
So if we have the sequence 1, 3, 5, 7, the corresponding series would be 1 plus 3 plus 5 plus 7, which equals 16.
You got it. The book explores different types of sequences, including arithmetic sequences, where the difference between consecutive terms is constant, and geometric sequences, where the ratio between consecutive terms is constant.
Okay, so an arithmetic sequence would be like 2, 4, 6, 8, because the difference between each term is 2. And geometric sequence would be like 2, 4, 8, 16, because each term is twice the previous term.
Exactly. And the book shows how we can use formulas to find specific terms in a sequence or to calculate the sum of a series. These formulas can be quite handy for solving problems involving patterns and growth.
I can imagine how those formulas would be useful in fields like finance or computer science, where you're dealing with lots of data and trying to identify trends.
Absolutely. Sequences and series are surprisingly versatile mathematical tools that have applications in a wide range of fields.
This deep dive into mathematical concepts has been incredibly eye-opening. We've covered so much ground, from basic number patterns and logic to complex algebraic equations, and even the intriguing world of irrational numbers.
Yeah, it's been quite a journey. And we've only scratched the surface of the vast and fascinating world of mathematics.
I'm feeling a renewed appreciation for this subject. It's so much more than just memorizing formulas and crunching numbers. It's a way of thinking, a way of problem solving, a way of understanding the world around us.
I couldn't agree more. Mathematics is a universal language that transcends cultural boundaries and connects us to the fundamental principles that govern the universe.
It's like a secret code that unlocks the mysteries of nature and reveals the beauty and elegance that lies beneath the
Oh,
surface.
exactly. And the more we explore the world of mathematics, the more we discover its interconnectedness, its depth, and its endless possibilities.
Well, dear listener, we hope you've enjoyed this deep dive into the world of mathematics. We encourage you to continue exploring the fascinating concepts we've touched upon today. There's a whole universe of mathematical wonders out there waiting to be discovered.
And remember, mathematics is not just for mathematicians. It's for everyone who's curious about the world and wants to understand how things work. So embrace the challenge, ask questions, and never stop exploring.
Until next time, keep those minds curious and keep diving deep.